All right, this is drill 5. As usual, the drill will be in the description, as will the answers to this drill. But let's just start forward with number 10. A toxic gas consists of 53.8% nitrogen and 46.2% carbon by mass. At STP, we have it occupy a certain space, 462 centimeters cubed. Determine the empirical formula of A, calculate the molar mass of the structure, and determine its molecular compound. So if we have 46.2% carbon and 53.8% nitrogen, we can just assume that instead of percents, we have grams divided by the molar mass, 12.01. 53.8 grams divided by the molar mass, 14.01. And when we do this math, we actually get the same answer, 3.85 and 3.84 moles carbon, mole nitrogen, which is pretty much the same in terms of your empirical formula. So we have C1N1. So when we look at this, we notice that this is honestly likely cyanide. So we don't really have to think about it too much. We're going to take out the ones because we don't write them in sides. So this is going to be cyanide. If we want to be more precise, assuming an ideal gas where 22.4 liters is equal to 1 mole, and in this case, let's use centimeters cubed, 22,400 centimeters cubed is equal to 1 mole. We can find that if we have that many centimeters cubed, and we just go ahead and take our value and do some dimensional analysis for 62 centimeters cubed, 22400 centimeters cubed, 1 mole, then we can find out from this that we actually 0.0206 moles. And if we have 0.206 moles and 1.048 grams, we can actually find the molar mass. We can find out how many grams per mole. And honestly, we can do that just by taking our grams, 1.048 grams, divided by our mole, 0.0206, and we will get an answer of about 51 grams per mole. Now, what this actually tells me, because I know that CN has a mass of about 26 grams per mole, that I actually need to double this. This will be C2N2, and that's going to be our answer. So we have to go through these checks to actually figure out what we have. Going through the actual check of taking our empirical formula and then running it through to confirm the molecular weight, or sorry, the molar mass, will give us the proper answer, C2N2, also known as cyanogen, which is also an incredibly toxic gas. So I'm glad we did the secondary check. Moving on to number 11, an oxide of copper was reduced in a stream of hydrogen. After heating, the stream of hydrogen gas was maintained until the apparatus had cooled. The following results were obtained. The mass of the empty dish, the mass of the dish and contents before heating, mass of dish and contents after heating, leaving to cool. Explain why the stream of hydrogen gas was maintained until the apparatus was cool. So for this first one, the stream of hydrogen gas has to be maintained because, oops, sorry. This reaction needs heat, and we want to ensure that we, one, don't have any backwards reaction. We don't want our product to react back, so we maintain this flow of hydrogen so that there is nothing to react with it other than hydrogen, which is going to constantly push it forward. So it needs heat, and we want to maintain the forward reaction. So for the second one, calculate the empirical formula of the oxide. We need to do a little bit of math. So first off, if we find the weight of our original thing, it's going to be 7.95 of our copper oxide. And we actually know because after we have reduced it all and we have taken all the oxygen out, we just have 1.60 grams of oxygen. From here, we can actually go ahead and figure out how much was copper by just doing 7.95 minus our 1.6. So we know that we actually had 6.35 grams of our copper, Cu. And then what we're going to do is go ahead and divide those by their molar masses. So this is going to be divided by 63.5, and this is going to be divided by 16. Oh, wouldn't you know, this becomes 0.1, and this also becomes 0.1 mole, which means that we have 1 Cu for every 1 oxygen. So it's CuO. The empirical formula of our copper oxide is 1:1 CuO. All right. C, write an equation for the reaction that occurred. Well, we know we had CuO, and we know we added hydrogen gas. So let's put our state symbols. And we know that we reduced our copper to Cu. And we must end up with the only product that comes from 2 hydrogens and an oxygen, water. Oh, sorry. So here is our balanced chemical equation. All right, lastly, D. Write something that we're going to state 2 changes that would be observed. So number 1, we're going to see a color change. Copper oxide, CuO, is black. Well, Cu, it's kind of like orangey, orange, gold, brown. It's copper. You know what copper looks like. All right, so we're going to see a color change, number 1. Number 2, if you look at our products here, we're going to get water, which will not be in its liquid state, sorry. It will be in its gaseous state. But on a tube, on the inside of a tube, we might get some condensation. So we'll probably see condensation inside the tube. This will also kind of inform you back on number 1. What are we going to see? Why do we need to keep the hydrogen gas flowing as we keep the temperature up? We want to make sure that that hydrogen gas will push out all the water so we don't get any of the backwards reaction. We don't want to reoxidize the copper. And if copper is maintained at that temperature, it will reoxidize when exposed to water. So we want to keep that hydrogen gas flowing. And with that, we have finished this question. All right.